Hello everybody, so I thought I'd go through the Google form, the answer to this, and sort of how you can work out the answer. So we've got question by question, and let's get started. So in a redox reaction, what happens to the reducing agent? So we've got a couple of options here, 4 options. It is oxidized, gaining electrons, and so on and so on and so on. So let's take an example of an equation here. Let's say we have chemical X, and chemical X goes to X positive. And the way that it goes to X positive is it has to lose an electron. So what's happened to chemical X here? Well, chemical X here has lost an electron. So we can say that this chemical here has been oxidized. If it has been oxidized, it is therefore the reducing agent. So in a redox reaction, what happens to the reducing agent? So the reducing agent in any reaction, the reducing agent equals oxidized equals loses electrons. And we can have maybe another example here. Let's have an example of chemical Y. This time it's a negative ion, and it just becomes, not X, sorry, it just becomes Y, the atom. And again, it's lost an electron. So this here is lost an electron, therefore it has been oxidized, therefore it is the reducing agent. And the opposite of that, of course, is an oxidizing agent. So let's do a third example if we've got enough space. Let's see, let's just do chemical A. And let's have this as a positive ion. This now gains an electron, and it becomes the atom A. Well, what's gone on here? Well, this here has gained electrons. So it has gained electrons, which means it has been reduced, which means it is the oxidizing agent. So if we just go and have a look at these, which does this fit for the reducing agent here? Well, reducing agent is oxidized, so we can therefore get rid of these two because that's saying reduced. We're not interested in those. Oxidized, and it loses electrons, oxidized and it gains electrons, well, that there must be the correct answer for that one. So hopefully that helps with a little bit there. I think it's this bit here that you can kind of keep this in the back of your head all the way through. So reducing agents are oxidized, and you sort of have to flip it around, don't you? So reducing agents, the opposite happens, almost it becomes oxidized and that loses electrons, and then oxidizing agents become reduced, which means they gain electrons, and then just sort of go from there and have a look at the individual chemicals and what's actually happening to them. And remember, please, that we're only ever talking about the reactants when something is oxidized or reduced. We're never talking about the products here. Okay, so that's question number 1. Okay, so next question. Hopefully you can see this. You might have to zoom in a little bit on yours. So which ion is oxidized in the above reaction? So what do we have? Well, we've got the Hg, and that is bonded to 2 lots of the chloride. So it's an ionic chemical. So therefore our ions present here are the Hg plus and 2 lots of the Cl minus. We've also got SnCl2. So SnCl2 as well. So what do we have here? So let's just draw a line under that. Well, that equals, again, we're going to have 2 lots of the Cl minus, because the chloride ion is always Cl minus, 2 lots of them. If the overall charge on this is neutral, that must mean that this is also Sn2 plus. Okay, so that's what we're dealing with here. Again, which ion is oxidized? We're not interested in these over here, so we don't have to worry about them because they are not being oxidized or reduced. They're just the products that are being made. So here are ions that we have present. We've got in total in this reaction, we've got a H plus, we've got Cl minus, and we've got Sn2 plus. So let's have a look at what we've got. We've got Sn4 plus here. Well, that isn't one of the ones that we have, so that's gone. Our Cl minus, well, our Cl minus here, it starts off as Cl minus, but what does it turn into? Well, this Cl4, well, we know our chloride is always going to be Cl minus. We've got 4 of them. The overall charge is neutral, therefore this must be 4 plus, but that wasn't really what we're after there. What we're after here is the point that the Cl minus here is the same here as it is down here. So it's the same as at the end of the reaction as it is at the beginning of the reaction. Therefore, this is referred to, you may remember, in this case the Cl minus is referred to as a spectator ion. Okay, so we're slowly getting there. What else? Sorry, that should be Hg2 plus. So what else do we have here? Well, we've got these two chemicals left now. So what's going on? Well, let's have a look at the Hg2 plus. So this one first of all, so we do that can be number one that we'll look at here. So the Hg2 plus, what is that turning into? Well, eventually that's turning into Hg, so the mercury here, so Hg is for mercury. How does it go from 2 plus to neutral? Well, it must gain 2 negative electrons. So let's have a think, what's gone on here? So this Hg has gained electrons, so therefore we can say that the Hg2 plus, let's do one in here actually, we can say that this here has been reduced, and if we wanted to, we could also therefore say that this is the oxidizing agent. And what's the other chemical that we're interested in? SN2 plus, so that is here, isn't it? So it's this one here, so number 2. So that goes SN2 plus, and let's have a look at what it's turned into. So it's turned into the SN, and this time it's the 4 plus. So tin SN2 plus has gone to SN4 plus. Well, how's it done that? Well, to become more positive, you have to lose something negative, and it has lost 2 negative electrons. So we can therefore say that this here has been oxidized. It is therefore the reducing agent. So that is the answer for this one here. It would be B. Okay, moving on. I think we're going to be here a while at this rate, so what I'll do is I'll put timestamps in the YouTube link so you can have a look at those and you can skip on to the questions that you are struggling with. So which of the following reactions is a positive ion reduced? So positive is key. So one of the things that is important when you're doing questions, remember, is to underline key words. So positive and ion and reduced there. So let's have a look at iodide here. So it's 2I minus, and that's going to iodine, which is I2. So regardless of what's going on here, we're talking about a negative ion, so we can get rid of that straight off. Let's do the sulfate here. Well, we'll do the sulfate last actually. Cobalt next, that's A, B, C, and D. Cobalt, so CO3 plus, and it goes to CO2 plus. How does that happen? How does it go from this positive to slightly, it has to gain an electron. So we'll come back to that in a second. So Ni2 plus goes to Ni3 plus, and the way that has happened, it has lost that electron there. And then down at the bottom here, SO4 2 negative goes to SO3 2 negative. And if you don't know how to balance this, get yourself a copy of the data book here and you'll find the equation in here. We'll look at this in a bit more detail for a question later on. So how does this work out? Well, we've got an imbalance of oxygens here. We've got 4 and we've only got 3 here, so we need to put a H2O. We've now got 4 oxygens on this side. We've got 4 oxygens on this side, but we've got our 2 hydrogens. So 2H plus here to balance the hydrogens. Now our charges are imbalanced. We've got a neutral charge on this side and a 2 minus on this side, so we need to add 2 negative electrons. And also, I suppose I should have said really at the beginning, this is a negative ion, so that's not going to be answered because we need a positive ion here. So we can get rid of that as well. Next, so we're looking at these last 2 here. Put a little box around that. Okay, so what's going on here? So positive ions, so they're both positive ions, reduced. Well, if you remember that reduction is gain of electrons. Well, this one here has gained an electron, so therefore this must be, we can say that the CO3 plus has therefore been reduced. The Ni2+ here, turning into Ni3+, well, that's losing an electron, so we can say that this here has been oxidized, so therefore the correct answer is this one here. Right, what I'm going to do now, I'm going to pause this video, upload this one, and then the later questions, we'll do it in little sections, otherwise this video is going to go on for about half an hour. So that's the first part. The second part will come up soon enough. Okay, so this is part 2. So the next set of questions are all about oxidizing and reducing agents. For the following reactions, identify whether each of the underlying reactants, so reactants there, is acting as an oxidizing agent or a reducing agent. So before I would start this question, is I just sort of get it straight in my head. What exactly do I mean by oxidizing a reducing agent? I don't think it hurts to have this written down. So if you're doing a test or an exam or whatever, just write it down so you've got a reference point. So let's do it down here. Let's say that our oxidizing agent is being reduced, which means it is gaining electrons, and our reducing agent is being oxidized, which means it is losing, and we're always talking about the reactants, remember, so it's always on this side. So let's take a look at this here, this Zn. So what does the Zn turn into? Well, we start off with the atom. We eventually end up with the ion form. So how has it gone from Zn to Zn2+? Well, it must have lost electrons. And so what's happened here? So this Zn here, well, it's been oxidized. It's lost electrons, it's been oxidized. Therefore, this here is the reducing agent. Okay, next one. I wonder if we can get that sort of in the corner. I'll do it again down here. So oxidizing agent equals reduced equals gain. Reducing agent equals oxidized equals loses electrons. Okay, so next one. What have we got here? Cl2. So we've got Cl2 goes to 2Cl negative. Well, how has something neutral become something negative? Well, the only way that can happen is if we gain electrons. So what's happened to this Cl2? That's the thing underlined. It has gained electrons, so gain down here. It has therefore been reduced. Therefore, this here, the Cl2, is the oxidizing agent. Now, just a little point to highlight here. Notice in both of mine, I'm not trying to work this out in my head. I'm writing out the equation for it. And that's something I would recommend that you guys do. So when you're doing these questions, get yourself a pad of paper and start to work them out. Don't try and do this in your head. I don't think that would be sensible at this stage. It's not one that I would do myself, even having taught this for years. I would still go out this way here, and I'd recommend you guys do the same thing. Okay, next one. Again, so just to remind ourselves, oxidizing agent equals reduced equals gained. Reducing agent equals oxidized equals lost or loses. Okay, so we're talking about Mg plus. No, we're not. We're talking about Mg, and that is turning into Mg2 plus. This magnesium here must have lost electrons. So therefore, losing electrons, oxidized, therefore this is the reducing agent. Okay? And just one thing to point out here as well, notice the charges. This might help you if you're struggling to figure out, to write these ion-electron equations. Look at the charge on this side here. The charge on this side is 0, it's neutral. The charge on this side here is also neutral. And that's the same for these. Well, it's not the same charge, but the charges are balanced on both sides of the equation. On this side of the equation, it's 2 negative. On this side, it's 2 negative. So when I'm adding electrons, I'm trying to balance the charges on both sides. And I think that works for this one here as well. Charge on this side of the equation is neutral. Here we've got 2 plus and a 2 minus added together, so it is also neutral. So that's just one thing to sort of remind yourself to help you when you're actually trying to work out these ion-electron equations, or data book. Okay, next one. So carbon monoxide. Well, what's that turned into? It's turned into CO2. But really, the cheat for this one is that there's 3 chemicals that you're required to remember as to whether they're oxidizing and reducing agents, common ones. And this one here is your reducing agent. But I wonder if we do the equation, it might not work. It's a bit more complicated because we've got balance. We can have a go anyway. CO2. How do we go from this to this? Well, we need to, oxygens, we've got an imbalance here. Okay, so we've now got, so we need 2 of those. So therefore we need 4 H pluses, and we therefore need, so CO, so let's just check the balances. 1, 2, 3, oh no, sorry, it was 1. That's stupid. 1, 2, 1, 2. 2 of those, 2 of those. Over here, our charge is neutral. Over here, it is now neutral as well. So what has happened here? Well, this chemical here, we can say that it has lost electrons, therefore it has been oxidized, therefore this is the reducing agent, which kind of fits what we were saying earlier on. Okay, let's have, I think this is the last one for this little section. Where are we? So again, oxidizing agent equals reduced equals gains. Reducing agent equals oxidized equals losers. So we have UF4. What's happening to this here? This is a bit tricky, this one, isn't it? So UF4 goes to the F2. Well, let's just have a look here. So the UF4, so that's going to be 4 positive, and this therefore is going to be 4 negative. So we can take each of these individually, I suppose. The U4 plus goes to U. It must have gained 4 electrons. So therefore we can say that this here has gain electrons have been reduced, therefore this is the oxidizing agent. Our F negative here is the same on this side over here. So we have this chemical here, let's do it up here. So the ionic formulae will be Mg2 plus and 2 lots of the F negative, and it's balanced, so we'd actually have 4 lots. So this here is F negative here and F negative here, so therefore these are spectator ions. So we're talking only really about the uranium 4 plus ion, so therefore that is the oxidizing agent. Okay. Okay, next question. So this is now going back to the data book, and I know a lot of you were, or some of you were asking in the feedback section, how to actually work out if something is a reducing agent or an oxidizing agent using the electrochemical series. So we've got this here. So I'm just going to check my camera, see if you can see this. That looks just about okay. So what I would do is when you've got your data book, first off, I print off a copy for yourself so you can get that. It's up on the class notes section or the useful materials section. And I'd write on it, I'd annotate it, because you can do what you want with it when you're in using it at home. If you're doing it exam, you get a different copy, but here we go. So what I would write up here, so these chemicals here, lithium, for example, that lithium here is not very electronegative. It's not able to hold on to its electrons, so it loses its electrons easily. If something loses its electrons easily, it is being oxidized, therefore it's a reducing agent. So these guys up here, they're really good reducing agents. And if these are our really good reducing agents, then this mean here that these are oxidizing agents. So let's have a look at the example of, you can't see that, can you? Let's have a look at the example of fluorine. So F2 right down at the bottom. Well, that F2 there is highly electronegative. it is going to gain electrons, so it's going to be reduced, therefore it's an oxidizing agent. So all of these down here are highly electronegative, either, well, these are elements, these are compounds here, but these are really able at taking electrons. So they're going to take electrons, they're going to be reduced, therefore these are oxidizing agents, whereas these ones up here are not able to hold on to their electrons, they're going to be oxidized themselves, therefore they are good reducing agents. And if we remember the rule for whether a chemical reaction will take place, we need to have our reducing agent on this side being higher than our oxidizing agent for a reaction to take place. So we'll come back to this in a second. Let's have a look at this though. Which of the following is the strongest reducing agent? So we're looking for something on this side over here. It can't be on this side here. These are all of these chemicals here are being reduced, therefore this K plus here is an oxidizing agent. So we're looking only on this right hand side over here. So fluorine, well, fluorine is F2, so maybe it helps to write this in. Lithium is Li, calcium is Ca, and iodine is I2. So fluorine is F2. Well, that's right down at the bottom here, so that's gone. That's not going to be the strongest reducing agent. Lithium, well, you maybe see where this is going already. Lithium's all the way at the top up here, so it's definitely a reducing agent. Where's calcium? Calcium is here, and iodine, so calcium's lower than the lithium is, and iodine is down here. So iodine and fluorine are both oxidizing agents. We want reducing agents. Which is the strongest reducing agent? Well, it's basically which one is the higher up this electrochemical series. So lithium is ahead of calcium, therefore lithium is the correct answer. So last two questions for this little section. Which of the following is most likely to act as a reducing agent? So we're looking for something on this side here. Well, let's try and find these chemicals. So on this here, because that might help us straight off. Well, our MnO4, our permanganate ion, is right down here. Just check, can you see that? You should be able to. Yes, yeah, so MnO4 negative is right down here. These are oxidizing agents, so, and we want reducing agent. So you're gone. Cr2O72 negative, the dichromate ion, again, it's right down here. It's an oxidizing agent. So that's gone too. Now we're left with the last two here, the peroxide and then carbon monoxide. I don't think that they're on this here at all. But again, this is one of the ones that you're expected to remember, that this here is an effective reducing agent and this here is an effective oxidizing agent. So this is pretty good at losing electrons, this is pretty good at gaining electrons. Okay, so the answer therefore is 10. No, it isn't. The answer therefore is A. Right, last one for this little section. Which of the following ions could be used to oxidize sulfite, that's this, to sulfate, which is this here? So let's remember our rule that our reducing agent needs to be higher than our oxidizing agent. And if we sort of sketched our electrochemical series, our reducing agent is over here and our oxidizing agents are on this side here. And we're looking for the reducing agent being higher than our oxidizing agent here. So for example, I don't know at the second, we'll have to look at this in a minute, but let's say that our sulfite is here on the electrochemical series. If this here, this Cr3 plus, if that's all the way up here, well, that's no good because our reducing agent has to be higher than the oxidizing agent. Let's say though that we find this chemical, let's say that's down here, in other words it's below, then that would work. So let's now take a look. So first off, let's find this equation. Well, it is, I think this is the last one, so let's start scribbling on this now. It's here, okay? So there is our sulfite. So it's the reverse here, so the equation is reverse, because remember all of these are reduction equations, so you can flip them around if necessary. So this equation here, this equation is just the total opposite of this equation. But here, so this now is on the reducing agent side. So we're looking for something which is here. If it's above, it's not going to work. So above here, that's not going to work, and down below, that is going to work. So let's look at them each individually. Cr3+, let's try and find that. That's down here. Well, that's on the same side. So this is also acting as a reducing agent. You can't have them be in the same side. They have to have one here and one here. One to lose electrons and one to gain electrons. Al3+, that is here. So it's above, so that doesn't work. So that one doesn't work. Fe3+, now come back to this because that's the answer. I'll explain why it's the answer in a second. Sn4+, let's try and find that. That is just above. That's above, so that is gone. Now the Fe3+, well, you may notice that this here, we have Fe3+, but we also have Fe3+ here. This Fe3+, I know it's really difficult for you to see, so I'm hoping that you guys, I can't zoom it down anymore without the whole thing. Well, maybe I can. Okay. So this Fe3+ here, let's have a look. That's gaining 3 electrons to become the atom, whereas this one here is only gaining 1 electron to turn into the Fe2+. So this version of ion where it only gains, or this situation for ion where it only gains 1 electron is going to be perfect for to be used as an oxidizing agent for the oxidation of of SO3 to negative. So which of the following ions could be used? Can you now see that? I think you can. Let me just get my clamp stand back up. Which of the following ions could be used to oxidize the sulfite? We're looking for this one. Okay, so that's part 2 finished. And the next part will be the last few questions, all to do about these things here, the ion electron equations and the balance of electrons and all that sort of stuff. Okay, so come back to that if you wish to. Right, here we go. So this is part 3. So the last 3 questions, these by far and away the most trickier things you have to do for this redox stuff. So let's show how you do it. So during a redox reaction, the nitrate ions, that's these guys here, NO3 negative, are converted to nitrogen monoxide, NO. Which line in the table correctly completes the ion electron equation? So basically you have to build this up. So remember, there's a series of rules for how you do this, what it is that you add, when you add them, and so on and so on. So it might be wise when you're doing these questions to have that tab open, the PowerPoint, or the video rather, have that video open where it shows those rules, and then you just follow them step by step. So what do we have to do here? So look, we got our ends, our nitrogen atoms here, nitrogen atom here, they're fine, so they're all right. We don't need to balance those. Our oxygen atom here, so O3, we've got 3 of them, we've got just the one over here. So we need to get some more of those. So the way that we get more oxygens is we add water. So we add H2O, and we've now got 2, we need 3, so we'll stick another one of those in there. So now we've got 1, 2, 3, 1, 2, 3, they're all good. Our new problem now is we've created a problem with the hydrogen. So we've got 4 hydrogen atoms over here. So let's stick a 4H+. And our next thing is we've got an imbalance of charges. So over on this side, we've got like an overall neutral charge. There's no negatives or positives here and there, so the overall thing is neutral. Over on this side at the minute, it's -1 and 4+, so overall it's 3+. So we need to get this side here down to the same as this one, down to neutral. So the way that we do that is we stick in some more electrons. And that now should, once we finish this bit, so at the minute, when I'm doing this, if I was doing this question, I wouldn't even be looking at this to begin with. I'd just be working out the answer and then seeing what does this fit with this here. So 4H+, 3E-, and 2H2O, that's this one over here. All right, so this is, in case it doesn't really say in the question, it doesn't really matter, but this here is a reduction equation. So this here is being reduced and is forming this over here. So that's the first one. Next question. During a redox reaction, the dichromate ions, that's these here, are oxidized to chromium ions. To balance the equation, what is the value of X? Right, 2 ways to do this. The practice one I suppose we could do is let's just rewrite the equation. This is obviously, there's going to be a much quicker way to do this, but I'll show you this way first. Good bit of practice. 14H plus E minus, we don't know how many yet, goes to 2Cr3 plus 7H2O. Can you see that? Yes, you should be able to. Okay, so what do we have on this side of the equation here? What's the overall charge? Well, these don't contribute anything at all. We've got 2 times the 3 plus, so in total we've got 6 plus. And over on this side, what we've got 2 negative and 14H plus. We'll actually just get rid of that for a minute because it's a bit confusing. So overall, we've got 12 plus on this side, 6 plus on this side. So we need to get this side down to 6 positive. So in other words, we need to add 6 negative electrons. So 6 E minus, and then that takes us to 6 plus. We're now all good. So 6 E minus is the answer. So that's the long way of doing it. Quick way to do it. Find that in the data book. This equation here, let's lift this up so you can see it. Let's get that into focus. There we go. We see it's the fourth one from the bottom. So Cr2072 negative plus 14H plus 6E minus. All right, so it might be worth just checking your data book whenever you get these if you're asked a question like this. Okay, because we do have, let's just do that. We do have quite a few of them down here. Okay, next. The ion electron for redox reactions are this one and this one. So what's this here? We've got the iodide is turning into iodine and it's losing 2 negative electrons. So this one here is, we say that the iodide is being oxidized and the permanganate is gaining some H plus ions and some, why is the negative gone there? And some 5E minus. So this one here is therefore being reduced. How many moles of iodide ions are oxidized by 1 mole of permanganate ions? I think I put this one up in the Google Forms already, but let's just do it anyway. Well, we can't add these two equations together, the ion electron equations. We can't do it because we've got 2 electrons here and we've got 5 electrons here. So what we need to do is we need to times everything here by 5 to get us 10 electrons and everything here by 2 to get us 10 electrons here. And if we do that, we get 5 times that, so we get 10 I minus, 2 times 5 is 10. Let's do this here. So how many permanganates do we get? We get 2 times, so we've got 2 MnO4 negative plus 2 times 8, 16 H plus. So what I've done now is I've taken all of the reactants and I've added them together, so that's there on this side here. Haven't included the electrons because the electrons here will be 10 on this side and 10 on this side, so they cancel. So I don't add those to an equation. What do we have next? We've got, it's getting a bit messy this, I do apologise, but there we go. 5 lots of the I2 and 2 times the Mn plus 2 times Mn2 plus 2 times 4 is 8 H2O, like so. So what is the question asking? So let's have a look here what we've got. We've got 10 moles of iodide reacts with 2 moles of permanganate and 16 moles of hydrogen ions to produce 5 moles of iodine, 2 moles of manganese and 8 moles of water. So this is a balanced redox equation here. But how many moles of iodide ions, that's the I minus, are oxidized by 1 mole of permanganate? The permanganate is MnO4 negative. Probably knew this permanganate to you. Google it if you're not too sure. Be a bit resourceful, use your initiative, stick it in Google, see what comes up if you get any terms, any chemicals you're not too familiar with. Do that for structures as well, with different types of questions. Anyway, so if here we have 2 moles, so we've got 2 moles of the permanganate, well, they will react with 10 moles of the iodide. We don't want that. We want it if we've got 1. So let's change our ratio. 1, well, if it's 10 to 2, 1 will react with 5. Therefore, our answer is 5 there. Okay? So that's that one. The next one I think is very similar. Let's have a look. How many moles of NO3 negative, so the nitrate, that's this here, are reduced by 1 mole of zinc? So we have 3 electrons, we have 2 electrons. So here's our reduction ion-electron equation. This is our oxidation ion-electron equation. We want to get a redox equation. We do that by adding them together, but we can't because we have an imbalance of electrons. So let's times everything here by 2. And let's times everything here by 3. And let's see what we get. So let's stick a 2 in front of that. 8, 6, 2, and 4. Everything here by 3. 3 lots of that, 3 lots of that, 6. Let's add this together now. So let's do the reactants first. First off, let's just get rid of those, actually get rid of those electrons. So let's do all of our reactants. So all of these here are going to go onto one side of equation. 2NO3 negative plus 8H plus 3Zn. So that's all of those. Now let's do all of these, all of our products. Well, we don't really need to, but why not? Plus 3Zn2 plus 4H2O. Now let's look at the question. How many moles of NO3 minus are reduced by 1 mole of zinc? Right, so it's that 1 mole there. Let's have a look at our ratio at the minute. Our ratio at the minute is 3 moles of this, 2 moles over here, but we only want 1 mole. So we do 2 over 3. Okay, so our ratio is 2 to 3 here, so our ratio is therefore, it's the same, it's 2 to 3, so it would be 0.66 recurring to 1, or in other words, 2/3. So our answer therefore is A. There's something else I was going to point out, but I can't remember what it was. What was it? Nope, it's gone. Never mind. Okay, so when I was looking at the feedback that you were all putting up, all sort of stuff here. So this is the equations. Don't know how to charge the electrons. Last couple of questions. So the equations again. The equations. Last two questions. You know, it goes on and on and on. So I think the real difficulty that people were having was these sort of questions here. So when we come to do the study group tomorrow, I'm going to put some more of these type of questions, and let's see if you can work together to sort of solve the answers to these. Get in touch if you want me to go over any of these questions again. Happy to do that. And thank you for watching. Bye for now.